Hello and welcome to yet another video of Cornerstones of Math. Today we are going to draw some graph and it will be interesting. So on the xy plane, we have to draw the graph of absolute value of x plus y minus 1 plus absolute value of x plus y plus 2 times absolute value of x minus y minus 3 equals 0. And we have to calculate the area of the region enclosed by the graph. Now this looks quite complicated at first glance, but in fact, we rely on only one principle as to how we remove the absolute value notation. The principle is that the absolute value of something must be always positive or 0. Therefore, if a is positive or 0, then absolute value of a is equal to just a because it is positive or 0. And if a is negative, then absolute value of a is equal to minus a because now minus a is positive. But even with this pro tip, it doesn't look that easy because we have 3 different types of absolute values here. And we even have the absolute value inside the absolute value here. But just like so many other math problems, when the problem is complicated, we can just start from what we can deal with. For example, many of you can at least deal with these 2 absolute values simultaneously. We do not think about this one for now. So if you only consider the signs of x plus y and x minus y, then we can think of these 4 cases. The first case is when both x plus y and x minus y are greater than or equal to 0. The second case is where x plus y is greater than 0 but x minus y is less than 0. The third case is when both x plus y and x minus y are less than 0. And the fourth case is where x plus y is less than 0 and x minus y is greater than or equal to 0. These are all very nice, but I want to express these conditions in a slightly different manner. That is, I want to express these as a comparison between y and minus x and a comparison between y and x. For example, the equivalent condition for case 1 is y is greater than or equal to minus x and y is less than or equal to x. And the equivalent condition for case 2 is y is greater than or equal to minus x and y is greater than x, and so on. The reason why I expressed cases like these is because then we can easily visualize the regions corresponding to each case on xy plane using 2 straight lines y equals x and y equals minus x. For example, the region for case 1 is the region that is above the graph of y equals minus x and below the graph of y equals x. Therefore, it is this region. The region for case 2 is the region above both graphs of y equals minus x and y equals x, so it is this region. And the same logic goes for cases 3 and 4. So now that we visually recognize the region for each case, let us investigate how the equation of the graph changes from region to region. First, when both x plus y and x minus y are greater than or equal to 0, or equivalently above y equals minus x and below y equals x. Since both x plus y and x minus y are positive or 0, the equation becomes absolute value of x plus y minus 1 plus x plus y plus 2x minus y minus 3 equals 0. So it is absolute value of x plus y minus 1 plus 3x minus y minus 3 equals 0. And now we have to consider this remaining absolute value of x plus y minus 1. It is not that difficult really. We just need more case division, now depending on the sign of x plus y minus 1, which gives these 2 cases. Case 1.1 is where x plus y minus 1 is greater than or equal to 0, or equivalently, y is greater than or equal to minus x plus 1. That is, above the line y equals minus x plus 1. Case 1.2 is where x plus y minus 1 is less than 0, that is, below the line y equals minus x plus 1. Therefore, within the region of case 1, we divide into 2 regions using the graph of y equals minus x plus 1 one above the line and the other below the line. In case 1.1, the equation becomes, this part just becomes x plus y minus 1, so plus 3x minus y minus 3 equals 0, which is 4x minus 4 equals 0, therefore we have x equals 1. So we have this graph in the region of case 1.1, the vertical line x equals 1. In case 1.2, where x plus y minus 1 is negative, now we have minus x plus y minus 1 plus 3x minus y minus 3 equals 0. So 2x minus y minus 2 equals 0, which gives y equals x minus 1. Therefore, we have this graph in the region of case 1.2. And that's all for case 1. So now we move on and consider case 2, where x plus y is greater than or equal to 0 and x minus y is less than 0. Here, absolute value of x plus y simply becomes x plus y. So this plus x plus y. But absolute value of x minus y now requires minus sign when the absolute value is removed. So we have minus 2x minus y here. So now we have absolute value of x plus y minus 1 minus x plus 3y minus 3 equals 0. And now we need secondary case division, which is the same as case 1 by the way, since we have the same expression x plus y minus 1 here. So it is above or below this line y equals minus x plus 1. Hence we have these two regions. So for case 2.1, we have x plus y minus 1 minus x plus 3y minus 3 equals 0, which gives 4y minus 4 equals 0. So we have y equals 1. So we have the graph of y equals 1 here. And for case 2.2, we have minus x plus y minus 1 minus x plus 3y minus 3 equals 0. So minus 2x plus 2y minus 2 equals 0, which gives y equals x plus 1. So we have the graph of y equals x plus 1 here. Now for case 3, and at this point you may have well understood what you should do. Since both x plus y and x minus y are negative, we have absolute value of minus x plus y minus 1 minus x plus y minus 2x minus y minus 3 equals 0. And this part is minus x minus y minus 1, but let us write it as the absolute value of x plus y plus 1 because it is a slightly simpler expression. And minus 3x plus y minus 3 equals 0. So now we divide cases according to the sign of x plus y plus 1. This gives two regions, one above the line y equals minus x minus 1, and the other below the line y equals minus x minus 1. So now we have to draw the graph of y equals minus x minus 1 and consider the regions above or below that line. For case 3.1, we have x plus y plus 1 minus 3x plus y minus 3 equals 0. So minus 2x plus 2y minus 2 equals 0. Therefore, y equals x plus 1. So we have the graph of y equals x plus 1 here. And for case 3.2, we have minus x plus y plus 1 minus 3x plus y minus 3 equals 0. Which simplifies to minus 4x minus 4 equals 0. So we have x equals negative 1. So we have the graph of x equals negative 1 here. We are almost done. As for case 4, now we have absolute value of minus x plus y minus 1 and minus x plus y and plus 2x minus y minus 3 equals 0. So we can write this part as absolute value of x plus y plus 1. Then we have plus x minus 3y minus 3 equals 0. So the subdivision is the same as in case 3, above or below the line y equals minus x minus 1. Above the line, we have x plus y plus 1 plus x minus 3y minus 3 equals 0. So 2x minus 2y minus 2 equals 0, which gives y equals x minus 1. So this graph. Below the line y equals minus x minus 1, we have minus x plus y plus 1 plus x minus 3y minus 3 equals 0. So minus 4y minus 4 equals 0. So we have y equals negative 1. So this graph. Therefore, in the end, we have this graph. And finding the area of the region enclosed by the graph is easy. This part gives area 1. This part gives area 1. And this combined gives area 1. So the area inside the graph is 3. However, we are not done yet. So far, I have explained the most general method. But as for this specific problem, we can draw the graph in a much simpler way if we properly understand the symmetry of the graph. So we are going to investigate some symmetries, and there is actually a very easy symmetry we can find. In the given equation of the graph, suppose that we replace x with y and y with x. That is, we basically switch x and y in the equation. Then it is not difficult to find out that we arrive at the same equation. That is, the equation does not change if we switch x and y. What does this mean? Well, we can find the meaning if we think about the relation between these 2 points x, y and y, x. As you can see, x, y and y, x are symmetric with respect to y equals x. This means that for every point x, y that is on the graph of this equation, the corresponding symmetric point y, x is also on the graph, since y, x also satisfies this equation. Therefore, we know that the graph is symmetric with respect to line y equals x. So this is the first symmetry, and let us try to find another one. This next symmetry can be a bit confusing, so let us think on the figure first. Let us think about the symmetry with respect to line y equals minus x. This means that if this point x, y is on the graph, then this point over the line y equals minus x is also on the graph. But can you find the coordinates of this point so that 2 points are symmetric with respect to y equals minus x? Well, the coordinates are now minus y, minus x, because if this length is x, then this coordinate must be minus x, so it can be negative number. And if this length is y, then this coordinate must be minus y. Therefore, the condition for symmetry with respect to line y equals minus x is that if we replace x with minus y and y with minus x, it gives the same equation. And we can easily verify that it is indeed true. Therefore, our graph is also symmetric with respect to line y equals minus x. And let us identify one last symmetry before moving on to the next part, just for the sake of completion. This one is the symmetry with respect to the origin. And this one is also really easy. If these 2 points are symmetric with respect to the origin, then the coordinates of the other point must be minus x, minus y. And we can easily find out that if we replace x and y with minus x and minus y respectively, we arrive at the same equation. Therefore, the graph is symmetric with respect to the origin. So far, we have obtained these 3 symmetries. 2 line symmetries, symmetric with respect to y equals x and symmetric with respect to y equals minus x, and 1 point symmetry, symmetric with respect to the origin. Therefore, we can draw the graph like this. In our case divisions, which divided the xy plane into 4 regions, we only consider one of them, for example, case 1, and draw the graph for that case only. For case 1, I have already explained that the graph looks like this. Then, since the graph is symmetric with respect to line y equals x, we just flip the graph over line y equals x. Next, since the graph is also symmetric with respect to line y equals minus x, we then flip this graph over the line y equals minus x. And you can see that the third symmetry with respect to the origin, is also satisfied. And this is the method of drawing the graph utilizing both case division and symmetry. And that's all for today's video. Thank you for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.